Why hello there? Why hello there? Why hello there? Why hello there? Why hello there?
Let's see that one more time in slow-mo.
Okay, so this mass 1 with an initial velocity of v, is traveling this way. It collides with this one, m2, of initial velocity equals 0. And basically, and now for v final, this becomes 0, and this one is going to be moving this way at a final velocity of v, m2, and this is ta-da!
Okay, so now we're going to do an elastic collision problem. So let's say this is Gary with a mass of 200 kilograms with an initial velocity of 0 meters per second. And coming at him is going to be Eric in a cart coming at Gary with a velocity of 4 meters per second. And their mass collectively will be, let's say, 40 kilograms. Okay, so we're going to start with conservation of momentum, which means that the delta momentum is going to equal 0. So that means that the initial is going to be equal to the final. So in other terms, it means that the mass of the first object times the initial velocity plus the mass of the second object times their initial velocity is going to be equal to the mass of the first object with velocity prime plus the mass of the second object velocity prime. And here they gave us the final velocity for the second object, which is going to be 2 meters per second. So now we replace all the values. We're going to say mass 1 is 200 kilograms times 0 meters per second, which is going to cancel out later, plus 40 kilograms times their initial velocity, which is 4 meters per second. And you're going to keep the velocities both positive because they're both going to be going in the same direction. And then we're solving for our velocity final for the first object, so what Gary is going to be going at after the collision. So it's going to be mass 1, which is 200 kilograms times velocity prime plus 40 kilograms times the final velocity, which is 2 meters per second. Okay, so this cancels out. So now you get 160 is equal to 200 v1 prime plus 80. And then you solve that 80 is equal to 200 v1 prime. And then v1 prime is going to be 0.4 meters per second.
In the morning, gotta be fresh, gotta go downstairs, gotta have my bowl, gotta have cereal, seeing everything, the time is going, ticking on and on, everybody's rushing, gotta get down to the bus stop, gotta catch my bus, I see my friends, kicking in the front seat, sitting in the back seat, gotta make my mind up, which seat can I take? It's Friday, gotta get down on Friday.
Hey guys. Hi Richard.
Oh, Gary.
Wait,
Let's see that one more time in slow-mo.
Hey guys. Helen Chen.
Okay, so now we are going to go over inelastic collisions. So first off, we're going to have a block. So the before will just be a block moving in that direction with the initial velocity of 10 meters per second. And there will be a second block with 0 meters per second. And then this block, mass 1, will have a mass of 10 kilograms. Mass 2 would have 5 kilograms. And afterwards, the velocity of the first box will just equal 5 meters per second. And the velocity of the second one is unknown. So now we're going to write the equation. You know that the initial momentum will equal the final momentum, which is equal to times that final velocity. And you know, you can just start plugging in. It would just be 10 meters per second for that initial velocity times 10 kilograms plus 5 kilograms times 0 meters per second. And you know that is equal to 5 meters per second times 10 kilograms plus 5 kilograms times an unknown velocity. And when you solve it out, you know that the final velocity of 2 would just be 10 meters per second.
Let's see that one more time in slow-mo.
Today we're gonna learn about inelastic collisions. Okay. So as we previously mentioned, the main difference between inelastic and elastic is that for this one, kinetic energy is not conserved. So kinetic energy initial is not equal to kinetic energy final. And in most of these cases, it happens when one body, okay, so this is mass 1, the initial equals some value, and then it collides with M2, which is like that, and then they end up together, and then they move as one unit at the very end with a final velocity. But conservation of momentum is the key here. Okay, so conservation of momentum. So this is what we're going to use to help us solve our problems. And our most important equation and in some cases, this generally becomes because they stick together at the very end, and kinetic energy is not conserved in these cases because when they stick here, this internal friction causes a loss of kinetic energy. There are two of these types. So we have just the normal inelastic, and then we have the perfectly inelastic. But the main difference is that for this one here, perfectly inelastic, the max kinetic energy is lost. And there you have it. Yep.
So now we're going to practice a perfectly inelastic collision. So remember our friend Gary from earlier? Well, Gary has gone on a diet, a seafood eat food diet. So he now has a mass of 300 kilograms. And he's moving to the right with an initial velocity of 3 meters per second. Gary is running into his brother, super fit Richard, who has a mass of 100 kilograms and an initial velocity of 0 meters per second. So now we're going to start with our conservation of momentum. So delta P is equal to 0. So P initial is equal to our P final, which means Gary's original mass mass Gary v Gary plus mass Richard v Richard has to equal our mass Gary prime v Gary prime. Well, his mass hasn't changed, so we don't need to write that. Plus mass Richard mv Richard prime. But since they're sticking together, we're not going to write it like this. We're gonna write it like m Gary plus m Richard times v final. So we're looking for the final velocity that they travel at together. So we're gonna plug in our values and we're gonna get mass of Gary 300 kilograms times his initial velocity of 3 meters per second plus mass of Richard 100 kilograms times his initial velocity, which is 0 meters per second. So this will go away, is equal to 300 kilograms plus 100 kilograms times V final. So we have 900 divided by 400 is equal to our V final. So our V final is 9/4 meters per second.
For an elastic collision versus an inelastic collision. So in both cases, momentum is always conserved if there is no external force. No external force. But the biggest difference is that in this case, kinetic energy total is conserved, okay? And this means that 1/2 m1v1 squared plus 1/2 m2v2 squared equals 1/2 m1v1 prime squared plus 1/2 m2v2 prime squared. So basically the total initial kinetic energy is equal to the final kinetic energy. And then for momentum is conserved, we have that m1v1 plus m2v2 equals m1v1 prime plus m2v2 prime. Okay. And these are your most important equations for an elastic collision.
Hey guys.
Wait, are you supposed to be saying that?
Okay, so let's say we have Gary. Per second.
Wait, how do I run?
You have to run for longer and for like.
Wait, David, what are you doing?
David, you suck. You're not supposed to.
Run on that side! I don't know. Megan, move!
Running.
Be quiet.
So today, okay, and that is inelastic collisions. Actually, there are two. Go.
Okay.
No, you did the
How's my
elastic
hair?
collision problem.
You guys don't hear me, right?
I gotta stop writing it.
Just keep going.
Okay. Today. So now we're gonna practice a perfectly inelastic.
Okay, ready?
Woo! Let's go, Jenny.
It's not working.
Yeah.
That was a good hit, but 2 times that velocity.
You have to write big too.
Oh. Oh god. It's huge. Why,
I
hello
farted.
there. Why, hello there.
Yes.
Ready?
Why, hello there. Where are you looking?
Okay.
Why, hello there.
Okay, I'm ready.
Why, hello there.
This way? Okay, this way.
I think that was the second
Can
one.
we practice?
1 hour later.
Like,
What is she doing?